When you want to calculate the area under the curve, everything goes well if you can find an explicit antiderivative. In that case, you can use the second fundamental theorem of calculus. Now, there will be cases where you cannot find an explicit antiderivative. In that case, you go for plan B, which is to find an approximation of the area under the curve. We've seen that we can do this using Riemann sum, so basically by putting rectangles to approximate the area under the curve. There are other approaches. You could try to put trapeziums to approximate the area under the curve, and when you do that and add the area of the trapezium, that's called the trapezoidal rule. Another possibility is to approximate your curve, that's the blue one, by a parabola. This is called Simpson's rule. It's the one we will be dealing with here. The idea is the following. Say you want to approximate the area under the blue curve on the interval AB. What you do is find a parabola which goes through those 3 points, the endpoints of the interval of interest and the midpoint. And then you say that the area under the blue curve, which is the one you really want, and the area under the parabola, represented in pink here, are roughly the same. So this is easier said than done, because you do not know the equation of the parabola. Let's try to see if we can get a formula for the area under the parabola. So the equation of a parabola is a quadratic. So there are these 3 numbers, a, b, and c, which we do not know. But we know that the parabola goes through this point, called a. And that means that if you sub in a for x in this equation, you will get f of a. So that gives your first equation. And then you do the same thing for this second point and get this equation, and this one, and get this equation. 3 linear equations, 3 unknowns. It's possible to solve. It's possible, but difficult. So we ask some help from Maple. Maple gives us coefficients which look terrible, but we can find an explicit value for them. What we really wanted was the area under the parabola, so we ask Maple to calculate the integral between a and b of the parabola, and we get this formula, which doesn't look too bad. I rewrote it for you here. So, the area under the function is approximately equal to the area under the parabola, which is this. So note that this formula only depends on the value of the function, so you need to find these 3 values. You can see an h here. This h is the width of a panel, so h is this, so that's h, and that's also h. And that's the reason why this is sometimes called the 1/3 Simpson rule. So what you will do in practice is decide what interval you want to use, that's your AB. You calculate f of a by subbing in the formula for f of 1/2 of a plus b, the midpoint. Calculate those values and then sub in this formula. If your interval AB is fairly large, then the parabola may not be that close to the curve. So what you could do is actually use lots of parabolas. We'll see this in the example to come. In this example, we want to use Simpson's rule to approximate this integral, which happens to be the area under this curve. Using Simpson's rule with 2 panel, we'll start with 2 panel, means that we're going to be using a parabola which goes through those 3 points, and we're going to say that the area under the blue curve is roughly equal to the area under the parabola. And the area under the parabola will be obtained through the formula we saw earlier. Let's write this. The integral between 0 and 4 of exponential of minus x squared on 4 dx, so that's the area under the blue curve, is roughly equal to the area under the parabola, which turns out to be, that's Simpson rule, h on 3, so f of your first point, so your f of a here, a is 0, plus 4 times f of the midpoint of my interval is 2, plus f of the right-hand point, plus f of 4. In this formula, h is the width of a panel. It's this, so h is 2. So this is equal to 2/3. And to find out what f of 0 is, I will just sub in the formula for f. So I get exponential of 0, that's a 1. 4 times f of 2. So I'm going to sub in 2 in this formula. So I get minus 4 on 4. And f of 4, again I sub in this formula. I get minus 16 on 4, which means that by Simpson rule, the area is 2/3 of 1 plus 4 times exponential of minus 1 plus exponential of negative 4. That's the area under the parabola, and it's close to the area under the curve. If I put this in my calculator, I get 1.66. We realize that if we want a better approximation, it would be good to have more panels. So let's redo it, but with 4 panels this time. We are going to treat these 4 panels as 2 groups of 2 panels, and we will apply our formula on each of these 2 groups. So our total area is equal to the green area plus the blue one. Okay, so let's use Newton's method for the green area. This is h, the width of a panel, so that's 1. So our formula says h on 3, so 1 on 3, and then f of 0 plus 4 times f of the midpoint, 4 times f of 1, plus f of the endpoint on the right, plus f of 2, and this is an approximation of the green area. We repeat this procedure to approximate the blue area. The width of a panel is the same, so that's h on 3. The left-hand point of the interval is 2, so that's an f of 2, plus 4 times the image of the midpoint. For the blue area, the midpoint is 3, plus once the image of the point on the right. Now we can either simplify a little bit or sub in and then simplify afterwards. I think I'm going to simplify first. So I have an f of 0 coming from the green area, 4 times f of 1 coming from the green area again. And I notice that I have an f of 2 here and another one. So if I combine them, I get 2 times f of 2, then plus 4 times f of 3, plus f of 4. Now I'm gonna sub in. F is this function. So f of 0 is exponential of 0, that's 1. 4 times f of 1. F of 1 is that 2 times f of 2. If I sub in 2 here, I'm going to get a 2 squared, that's a 4. So I get exponential of negative 1, plus 4 times f of 3. So that's exponential of minus 9/4, plus f of 4, that's exponential of minus 16 divided by 4, which is this. Using our calculator, we get that this is equal to 1.736. And since we've been using more panels, the approximation is a little better. What we really did is to use one parabola here and another one there. To get an even better approximation of the area under the blue curve, this time we'll be using 8 panels. This is 4 lots of 2 panels. So for each of this area, we will be using Simpson's formula, meaning that we'll be using 4 different parabolas. The total area under the curve is the sum of the area A1, A2, A3, and A4. So that's my h, that's the width of a panel, and in this case, h is equal to 1/2. So Simpson's rule says h on 3. Then we're going to get, so that's 0, that's a half. So f of 0 plus 4 times f of 1/2 plus f of 1. And we do the same thing for the 4 panels. Something interesting is going to happen for the coefficients, and I would like you to notice that. Now let's look at A2, then A3, the green area, and finally we approximate A4. Again, image of the value on the left, 4 times the image of the midpoint, so here for a4 at 3.5 plus f of the right hand side. And we notice that several terms appear in two sums. F of 3 is in these two, f of 2 is in both, f of 1 is in both. So let's add these four formulas. First, let's see what we're going to do with those terms. What we could do, since we don't like to have fraction inside fraction, is to multiply the top and the bottom by 2. After doing this, at the top we get a 1 and at the bottom we get a 6. This is going to be exactly the same for all of those. So we have this 1, 6, and let's see what we have. So f of 0 appears only in the first sum here. F of 1/2 also appears in only one sum, 4 times f of 1/2. Now, as we said, f of 1 appears in both, so we get 2f of 1. Then f of 1.5 appears in only one sum, in the yellow one. F of 2 appears in two of them, so we get f of 2 twice. F of 2.5 appears only in the green sum. F of 3 appears in two of them. F of 3.5 appears in exactly one, the last one, the red one. And finally, f of 4 appears only in the last one. Take a look at the coefficients. This is a 1, 4, 2, 4, 2, 4, 2, 4, and 1. Your coefficients will always look like that. You will always get a 1 on the outside, and then when you go towards the center, you get a 4, and then it's 4, 2, 4, 2, 4, 2. I'm telling you so you can check your calculations. Now, if you calculate this sum using a calculator or a computer, you get 1.76413 using this approximation. And if you do it with Maple, look how close we are. That works really well. Thank you for listening to this video about how to approximate the area under the curve when you don't have an antiderivative using Simpson rule several times if necessary.